Ever wonder what keeps your car's engine from turning into a molten heap of metal on a hot summer day? There's a silent, hard-working hero tucked away in the engine bay, the water pump. Think of it as the very heart of your car's cooling system. Its entire job is to keep that lifeblood, your coolant or antifreeze mixture, constantly circulating. It sends this coolant on a critical journey, from the radiator through the scorching hot engine block and cylinder head to absorb intense combustion heat, then back to the radiator to cool down, only to start the trip all over again. Without this non-stop flow, your engine would overheat in minutes. So how does this humble pump actually work? Most modern cars use what's called a centrifugal pump, and it's almost always driven by the engine itself. At its core is a spinning fan-like piece called the impeller. This is what actually moves the coolant. The impeller spins inside a metal or plastic housing that directs the flow, and it's all mounted on a shaft supported by a sealed bearing. Now, that bearing is the most common point of failure. The whole assembly is turned by one of a few methods, most often by the engine's main serpentine belt, but crucially, on many engines, it's driven by the timing belt. Some engines with timing chains might still use a separate belt for the pump, and sealing it all in is a critical seal that keeps the pressurized coolant from leaking out and destroying that all-important bearing. Because it is a wear-and-tear item, it will fail eventually. Knowing the warning signs can save you from catastrophic engine damage. The most common tip-off is a coolant leak. You might see a bright green, orange, or pink puddle under the front of your car. Many pumps even have a designed weep hole that lets a little coolant out as an early warning before the main seal completely fails. A worn bearing often announces itself with a high-pitched whine or grinding noise that gets louder as you rev the engine. Of course, if the pump stops circulating, your temperature gauge will start climbing into the red, especially when you're idling. In severe cases, you might see steam rising from under the hood. A really worn pump might even have a visibly wobbly pulley, though never check that with the engine running. And here's a sneaky one. If your car's heater suddenly stops blowing hot air, it could be because a failing pump isn't circulating hot coolant to the heater core anymore. What causes this vital part to give up? Well, mostly just the miles. Bearings and seals naturally degrade, typically between 60,000 and 100,000 miles. But you can accelerate its death by using old, contaminated coolant that becomes acidic, or by using the wrong type of coolant altogether, which can corrode parts or damage seals. Air bubbles in the system, a problem called cavitation, can also erode the impeller over time with tiny, damaging implosions. And of course, physical damage from debris or a broken belt can spell instant failure. When it comes time for replacement, there's one golden rule you must remember. If your water pump is driven by the timing belt, you must replace the pump every single time you replace the timing belt. This is absolutely non-negotiable. The labor to get to it is essentially the same, and if the pump fails later, you'd have to pay for that huge timing belt job all over again. Whether it's timing belt or serpentine belt driven, always use a new gasket or seal and consider a full coolant flush with the manufacturer-recommended fluid. It's also a smart time to check any related belt tensioners or idler pulleys. As for the job itself, swapping a serpentine belt-driven pump can be a moderate DIY project, but a timing belt-driven pump is complex, advanced work where a timing mistake can destroy your engine. Costs can vary quite a bit. The part alone might run you $50 to $250. For a serpentine belt-driven pump, the total job often lands between $300 and $600. But if it's driven by the timing belt, the full repair with the timing belt kit can easily range from $500 to over $1,200. The good news is you can prolong your pump's life with smart maintenance. Your number one defense is to follow the coolant service intervals in your owner's manual, usually every 30 to 60,000 miles. Always use the correct type of coolant. Don't just mix whatever's on sale. Have your mechanic check for leaks and belt wear during routine oil changes, and train your ear to notice any new, unusual whining or grinding sounds. The water pump is a simple, vital component that doesn't last forever. Its failure doesn't just leave you stranded, it leads directly to engine overheating, which can warp cylinder heads, blow head gaskets, or seize the engine entirely in just a few minutes. Being proactive, especially by tying its replacement to major services like a timing belt job, isn't just smart maintenance. It's a core part of responsible car ownership. Of course, here is the rewrite for smooth video narration, incorporating all key points in a flowing, conversational style. Let's talk about how pumps are changing. While the traditional belt-driven pump is still common, the future is increasingly electric. Electric water pumps are now a key feature in many modern vehicles. Sometimes they're standalone units in performance cars, or they act as auxiliary pumps, like in some BMWs, where they can run after the engine shuts off to prevent heat soak. In hybrids and electric vehicles, these electric pumps have a huge job. They cool the battery pack, the power electronics, and the internal combustion engine when it's running. Their big advantage: they can run independently of engine RPM for optimal flow control, they reduce parasitic power loss from a spinning belt, and yes, they can operate even with the engine off. The trade-off is more complex electronics and reliance on sensors and ECUs. And it's not just how they're driven, but how they're built. Inside, you have impellers that can be open or closed. Closed ones are more efficient but can clog, while open designs handle debris better. And the material matters. You have traditional, durable cast iron, lightweight aluminum, or modern plastic composites that are corrosion-proof and quieter, though they can degrade in bad coolant or extreme heat. Now, to understand why they fail, we need to look at the physics inside. A bearing doesn't just suddenly break. It's a progression. It starts with the primary seal wearing down, often a ceramic or graphite face seal, allowing coolant to seep into the bearing grease. That coolant then washes the lubrication away, leading to corrosion and pitting on the metal components. As the damage increases, the shaft develops play, which finally leads to catastrophic failure. The bearing seizes, often snapping the drive belt, or it disintegrates completely, causing destructive wobble. But there's another silent killer: cavitation. This is when low-pressure bubbles form in the coolant on the suction side of the impeller, only to violently implode on the high-pressure side. These micro-implosions act like tiny jackhammers, eroding the impeller blades into a pitted, sponge-like surface. This dramatically reduces pumping efficiency long before you ever see a leak, and it's caused by things like a clogged radiator, excessively high RPM, or air trapped in the system. So how do professionals diagnose a pump that's on its last legs, but not dead yet? They go beyond the obvious symptoms. They might perform a flow rate test with an infrared thermometer, measuring the temperature difference between the radiator's inlet and outlet hoses. A small difference means insufficient flow. A pressure test can rule out other leaks and even reveal a catastrophic internal leak into the oil passages. They'll use a mechanic's stethoscope to pinpoint a worn bearing's whine exactly at the pump body, distinguishing it from other pulleys. And some even use thermal imaging cameras to spot cold spots in the engine block, revealing where coolant isn't flowing properly. It's also critical to see the water pump as a linchpin in a wider system. Its failure doesn't just cause overheating, it's the #1 cause of blown head gaskets in modern engines. Poor flow can lead to high oil temperatures by crippling the oil cooler, and it can cook a turbocharger's bearings after shutdown through residual heat soak. Even your transmission is at risk, as many cars cool their automatic transmission fluid through a heat exchanger in the same radiator that's now full of overheated coolant. This brings us to the world of performance. High-performance aftermarket pumps often feature impellers with more aggressive blades, tighter clearances for efficiency, and upgraded bearings like rollers instead of balls. Some racers even use underdrive pulleys to slow the pump down at high RPM to reduce parasitic drag, though this requires careful calculation to keep things cool at idle. And electric conversion kits are popular in hot rods, offering precise, belt-free control. When it's time for a replacement, you face a choice: OEM, high-quality aftermarket, or economy parts. OEM is guaranteed to match specs, but is expensive. Often, the best value is a high-quality aftermarket brand from manufacturers like Gates or Aisin. They're frequently the same companies that made the original part. Economy parts. They're a risky gamble with inferior castings and weak seals on a component this critical. A quick pro tip: if your original pump has a plastic impeller, upgrading to a quality aftermarket pump with a metal impeller can be a smart move for durability. Speaking of replacement, if your pump is driven by the timing belt, the job is 90% labor just to access it. Professionals follow a meticulous ritual, locking the engine timing with specific tools, fanatical cleanliness to avoid debris in coolant passages, perfectly cleaning the engine block mating surface, following a precise torque sequence on often tiny bolts, and most importantly, bleeding the system of all air, which is the #1 post-installation mistake and a fast track to damaging your brand new pump. Looking ahead, the future is about smart integration. We are already seeing smart electrically assisted pumps in cars from VW and Audi, where a belt-driven pump gets a boost from an electric motor for extra cooling when needed. And the cutting edge is fully integrated thermal management, like in Teslas and new BMWs, where a thermal control module treats the pump as just one actor in a network, directing coolant on demand to the engine, battery, cabin, and electronics with surgeon-like precision. The water pump is more than just a part. It's a dynamic seal and rotating assembly constantly fighting extreme heat, chemical attack, and mechanical stress. Its failure isn't an if, but a when. Understanding this, its deep role, its hidden failure modes, and the critical nature of preventative replacement is what separates an informed owner from someone who risks a $5,000 engine repair over a $150 part. Treating the cooling system with respect is how you keep the very heart of your car from having a meltdown. To truly master the water pump, we have to zoom in, weigh in, and then pull back to see its place in the grand scheme of engineering. This is where it gets fascinating. Let's start at the microscopic level with the science of failure. Inside a typical pump is a deep groove ball bearing packed with special high-temperature grease. Its downfall is a precise 5-act tragedy. It begins almost invisibly, with the primary seal's flexible lip hardening from countless heat cycles until a microscopic gap, thinner than a human hair, forms. Through this tiny breach, coolant, which acts as an electrolyte, seeps in. Inside the bearing, stainless steel balls and chrome steel races now form a tiny galvanic cell, starting a process of electrochemical corrosion. The invading coolant then reacts with the lithium-based grease in a process called hydrolysis, turning it from a protective gel into a watery or soapy mess that can't lubricate. With the lubrication gone, the incredible stresses where the balls meet the raceway cause microscopic fractures to spread, flacking off bits of metal called spalls. In the final act, these metal flakes circulate as an abrasive paste, vibration skyrockets, and the bearing meets its end. It either seizes instantly, often shearing the drive belt, or completely disintegrates, letting the shaft wobble wildly and destroy everything around it. The impeller tells its own story of struggle through distinct erosion patterns. Cavitation erosion leaves a signature, orange peel texture or deep pits on the pressure side of the vanes. Abrasive erosion, from contaminated coolant, shows up as parallel scour marks on the suction side. And if you see an aluminum impeller that looks uniformly thin and chalky, that's corrosion erosion from acidic coolant slowly eating it away. To understand a pump's health, engineers think in curves. Every pump has a performance curve, and the cooling system has a resistance curve. Where they meet is the operating point. A worn impeller drags that performance curve down, delivering less flow. A clogged radiator steepens the system's resistance curve, forcing the same pump to work harder for less result. Car makers cleverly design the system so that at cruising speed, the pump is only working at about 20 to 30% of its maximum capacity, leaving a huge reserve for when you're climbing a mountain on a hot day. The damage from a weak pump isn't always uniform. Thermal imaging reveals that cylinders 3 and 4, being farthest from the pump inlet, can run a staggering 15 to 25 degrees Celsius hotter than cylinders 1 and 2. This uneven heating can warp the cylinder head like a banana, causing a localized head gasket failure long before the dashboard gauge ever hits the red. And air in the system is a sinister foe. It creates a two-phase flow of liquid and gas that the pump was never designed for. This slashes cooling efficiency, causes destructive hydraulic hammer from compressing air pockets, and can even make the pump lose its prime entirely at high RPM. Now let's look at how this humble part is reimagined for extreme duty. In the high-stakes world of NASCAR and Formula One, the water pump is often gearbox-driven and integrated into the dry sump oil system. Companies like Stewart Components make racing pumps with aerospace precision, CNC-machined aluminum housings, ceramic bearings, and impellers balanced to within half a thousandth of an inch. Some Le Mans prototypes even use electromagnetic couplings to vary pump speed independently of the engine by up to 40%. Meanwhile, in heavy-duty industrial engines, you might find a replaceable cartridge bearing for easy service, or pump with dual impellers on a single shaft, one for the engine block, another dedicated to the intercooler. In marine engines, raw water pumps use flexible neoprene impellers that can survive running dry. And in small aircraft, the pump is gear-driven with a protective shear pin. If the impeller jams on ice, the pin snaps, saving the engine gears from destruction. When a failure leads to disaster, investigators become detectives. They examine the bearing for clues. Indentations called brinelling indicate a shock load. False brinelling suggests the car sat too long. Polished skid marks point to lubrication failure, and a blue tint reveals overheating. The impeller is a pattern book. Evenly eroded veins point to system-wide cavitation. A single damaged vein screams foreign object, and a melted plastic impeller is a telltale sign of a thermostat stuck closed. Even the coolant itself can be analyzed with atomic absorption spectroscopy, where traces of aluminum, iron, or copper act as a forensic report on what parts were being eroded. This brings us to the digital revolution. In a modern BMW, the electric auxiliary pump isn't just a pump, it's a smart CAN-bus device with its own computer. It talks to the engine, the climate system, and the battery management, and its algorithm can preemptively ramp up flow during aggressive driving based on throttle, gear, and even lateral G-forces. If it fails, the car enters a safe, limp mode without overheating. Tesla takes it further, dissolving the traditional pump concept entirely. Their system uses a low-pressure gear pump as just one actuator in a vast network managed by the brilliant octavalve, which can route coolant or refrigerant through any of 16 possible pathways to precisely manage the temperature of the battery, motors, and cabin. There are even esoteric phenomena, like coolant flow resonance, where at certain engine RPMs, pressure pulses can set up standing waves in the hoses, choking flow by up to 40%, a problem solved with clever impeller designs or helical coolant passages. The creation of a premium pump, like one from Aizen, is a masterpiece of manufacturing. It involves permanent mold casting, investment cast impellers balanced to an extreme standard, Swedish bearings packed with water-resistant grease, and laser-welded silicon carbide seals. Every single unit is tested at 6,000 RPM, verifying its flow, checking for leaks finer than a drop per hour, and ensuring vibration is virtually non-existent. Here's a beautiful paradox. Sometimes, a pump that's *2* efficient is a bad thing. In the first 2 minutes after cold start, the engine needs to get hot fast to reduce friction, enter efficient fuel control, and light off the catalytic converter. A pump that moves too much coolant too quickly wastes that precious heat out the radiator. This is exactly why thermostats exist, why smart electric pumps can dial down to 10% speed, and why racers in cold weather might use a restrictor plate. Gazing further into the future, we see concepts like magnetohydrodynamic pumps from Toyota and MIT, which have no moving parts and use electromagnetic fields to move coolant, albeit with a massive current draw. Or NASA's research with shape memory alloys, where wires heated by engine waste heat themselves contract to drive a pump, requiring zero electrical power, a perfect idea for a Mars rover. So what is the zen of water pump mastery? It's understanding that this component is, at once, a necessary compromise, a diagnostic sensor for the whole cooling system, a protective fuse for the engine, and a historical time capsule that records the life of your car. The final wisdom is this: A skilled mechanic replaces the water pump when it leaks. A great engineer asks why it failed after exactly 82,347 miles, traces it to a specific batch of coolant, and designs a better seal. Both perspectives are invaluable, but true mastery lies in holding both in mind at once, seeing the simple, spinning part and the universe of engineering it contains. We've journeyed past the manuals, beyond the repair guides, and through the engineering deep dives. Now let's step into a different space, a space where the humble water pump becomes something more. It becomes a lens, a prism, through which we can see the entire story of mechanical civilization, from its simple beginnings to its complex future. To understand where we're going, we must first see where we've been. The water pump's own evolution is a perfect map of automotive progress. It started in the thermosiphon era, before 1910, with no pump at all. Engines relied on faith and physics, the simple idea that hot water rises and cool water sinks. It was a faith-based cooling system that severely limited what an engine could be. Then came the gear-driven revolution. From the 1910s through the 1950s, the first true pumps emerged, often gear-driven right off the camshaft. They were positive displacement, robust, and loud, a design that shouted mechanical honesty. You can still hear this honest shout in antique tractors and some aircraft engines today. This gave way to the centrifugal epoch, the belt-dominated age from the 1960s to the 2000s. This was the mass-production golden age. The simple, cheap, effective centrifugal pump, driven first by a V-belt, then by a serpentine belt, powered the suburban revolution. And its universal weakness, that shaft seal and bearing, became the defining failure mode for a whole generation of cars. Today, we're in the era of electromechanical synthesis. This is the age of optimization, electric pumps, smart controllers, and thermal management modules. Here, efficiency trumps pure mechanical simplicity. The pump transforms from a simple spinner into a cybernetic organ, responding not just to RPM, but to data. And we're already glimpsing the post-pump horizon. In systems like Tesla's octavalve, the discrete pump vanishes. It dissolves into a fluidic computing matrix, where moving heat is no longer a mechanical task, but a software-managed problem of resource allocation. Now let's listen to the symphony this part conducts. A single water pump is the conductor for a vast orchestra of chemistry, materials science, and energy. It sits at the center of an electrochemical triad, a crossroads of three corrosive battles. First, there's the coolant chemistry itself, a careful dance of silicates, phosphates, and organic acids designed to protect aluminum, solder, and iron, all without degrading the seal's delicate elastomers. Then there's bearing tribology, where the grease's lithium thickener fights hydrolysis, the bearing steel's chrome oxide layer resists pitting, and the seal's Witten struggles against hardening. And holding it all together is the fight against galvanic corrosion, an aluminum housing bolted to an iron block, with only a cocktail of coolant inhibitors preventing them from eating each other alive. Beyond chemistry, there's an energy flow nexus. A traditional pump is a parasite, consuming 5 to 15 horsepower at high RPM, a direct tax on power and fuel, but it's also a redistributor. In winter, a functioning pump and thermostat direct waste heat to your cabin heater. Your comfort is literally a byproduct of controlled inefficiency, and it's a lifeline. For a turbocharger spinning at over 100,000 RPM, the pump's post-shutdown afterrun is what prevents coking, where oil turns to deadly carbon crust in the searing stillness. No pump, no turbo longevity. Beyond the formal diagnostics, there exists a realm of folk wisdom, of senses honed by experience. There's the hiss test. A seasoned mechanic, on a cold engine with the radiator cap carefully removed, might rev the engine just to listen for a hiss or gargle from the radiator neck, the sound of a sudden healthy surge of flow. There's reading the heater core pulse, feeling the inlet and outlet hoses for that subtle temperature difference that whispers of good circulation. And perhaps most poetic is reading the weep hole oracle. The pattern of the crusty coolant deposit tells a story. A fine spray indicates a slow, weeping seal. A single, heavy drip points to a wobbling shaft. A clean hole on a dead pump that tells of a sudden, catastrophic death. a bearing seizure, not a slow wear-out. This brings us to the deep, almost existential paradoxes the water pump presents. First, the robustness vulnerability paradox. The pump's design is brilliantly robust, a simple centrifugal device that can last 100,000 miles. Yet its single-point vulnerability is absolute. A seal breach thinner than a human hair or a single grain of sand in the bearing will destroy it. Its greatest strength and its fatal fragility are inseparable. Then the intelligence dumbness paradox. A smart electric pump can make brilliant, efficient decisions, but it is helpless without a web of sensors and a steady 12-volt supply. A dumb belt-driven pump is mindless, but it will work through an EMP, a failing alternator, a dying battery. So which one is truly more reliable? And finally, the cruel service neglect paradox. The single best thing you can do for a water pump is regular coolant changes. Yet to change the coolant, you must run the pump. This very act of maintenance forces the old, worn seal to face fresh, potentially more corrosive coolant and new system pressure. Sometimes, the maintenance designed to prolong its life is the very thing that finally ends it. The cure can be the assassin. Let's dream for a moment. If cost and complexity were no object, what would the perfect, platonic ideal of a water pump be? Imagine its material, a monocoque of silicon nitride ceramic, utterly immune to corrosion. Its bearing, a frictionless hydrodynamic air bearing. Its drive, a pure magneto-hydrodynamic field with no physical connection to the engine. Its seal, a laser-maintained boundary of plasma, a perfect zero-friction barrier. Its intelligence, an embedded quantum dot sensor reading the coolant's very soul. Its pH, its particulate count, predicting not just its own failure, but the health of the entire engine. This would be a pump that isn't a pump at all. It would be a field effect, an invisible, perfect director of thermal energy. After all this, the history, the chemistry, the paradoxes, and the dreams, we arrive at the final, unspoken truth. The water pump is a monument to accepting inevitable decay. Every internal combustion engine is a controlled explosion. The pump's job is to manage the inevitable, chaotic waste product of that explosion, heat, and in doing that job, it itself is subjected to the chaos. It wears, it leaks, it fails. We design them to be replaceable because we have accepted that nothing in this system is permanent. So replacing a water pump is not merely a repair. It is a ritual renewal. You are acknowledging the entropic nature of the machine and you are pushing back against it. For a time, you are giving the heart of the cooling system another 100,000-mile heartbeat so the engine can continue its fiery, temporary dance. To truly know the water pump is to understand the central dilemma of all machinery, how to create enduring function from components that are, by their very nature, transient. It is a lesson in humility, in care, and in the quiet beauty of things that work hard, fail gracefully, and allow us the privilege to try again. That is all we have for you in this video. Thank you for watching. If you enjoyed this video, don't forget to give it a thumbs up and subscribe for more automotive content. We love hearing from you, so drop your thoughts or questions in the comments below. If you have any suggestions for future topics, let us know. Until next time, drive safe and keep exploring the roads of automotive history.